in the Sustainable Pavement and Asphalt Research Group of the at the University of Antwerp, and his current project examines the oxidative mechanism of polymer modified bitumen in combination with the polymer deterioration over time. And in 2022, he was successfully awarded the title of, he could get his PhD at the same university, and his PhD dissertation investigated by a number of spectroscopic, microscopic, thermoanalytical, and rheological techniques for aging mechanisms of bitumen. And he also holds a master degree in civil engineering from Aristotle University of Thessaloniki in Greece, and a master degree in structural engineering with a specialization in road and railway engineering from Delft University in Netherlands. And so he has a very, very ambitious, I can say, researcher. We know each other for I'm saying for 2-3 years. If I agree, if I remember, I correct. And so he's very active researcher. He has authored and co-authored over 30 publications in highly esteemed international journals, has participated in multitude international conferences, and is also a member of several technical committees for testing and characterization of bituminous binders. He's also the European representative of the Global Antioxidant Consortium. And finally, he is also a founder of 30 early career researchers around the globe who established a young PhD researchers, a group community as called Young Aging Crew. The title of today's presentation, what Georgios will be delivered, is towards an enhanced understanding of the oxidative aging mechanism in bitumen. And before I give the floor to Georgios, for those of you who are for the first time are using Teams, in the first, we have 2 sessions in this webinar. In the first session, Georgios will be give his presentation, and following to that, we will in the second session, next session, we will have a Q&A session. I hope all attendees, especially our students, can actively participate and involve and discuss about what is going to be presented. So you can ask your question whether after the presentation by raising your hand and turning on your mic, and you can answer directly your question, or you can type your question in the chat box. When you click on chat, you can ask your question or type your question during the presentation or after that, and I would collect the question, and Georgios hopefully will answer to us. Okay, with that, I think with this introduction, I would like to thank Georgios again for accepting my invitation. And it's I hope today we will have a very fantastic and the presentation and discussion about the latest development in the field and in the field of asphalt material. Just I have to forgot to record this session. Now I stop to yeah, I think it's recording already, if I'm not sure. Recording.
Yes.
Okay.
I'm recording.
Okay, you record. Okay,
yeah,
great.
Okay.
So you're done. Thank you, Haibo, for everything. Okay, I will stop now sharing my screen and give the floor to Georgios. Georgios, it's your turn. Thank you.
Thank you very much, Dr. Rahman, for the invitation, and also I expand the thank you also to Dr. Ding for this invitation for today. So I'm gonna share my screen also. I hope you can all see my screen now in full mode, right?
Yes, we can see. Yes, we can see your screen.
Perfect.
Yes. Great.
So thank you very much once again for having me in this pavement webinar series of your university. And I hope that somehow this presentation can be interesting also for the students that they are attending this session today. As Dr. Rahman mentioned, my name is Georgios Pipintakos, and I'm nowadays a postdoc researcher at the University of Antwerp. Antwerp is located in Belgium, in the center of Europe almost. And my current project is funded by the foundation, the research foundation in Flanders, which is part of Belgium. My topic today is with regard to the aging of bitumen. Bitumen is the same thing that in other regions of the world is called asphalt binder or asphalt. So just the terminology is based on European, let's say, level. So bitumen, just to make it clear, is the asphalt binder that we use for pavement. So today I will talk with regard to the aging mechanisms of bitumen, and to ensure that this presentation will evolve smoothly, I have included some menu which I will go through it during my presentation. And in this menu, I have included some background. So what has been reported or hypothesized before with regard to the aging mechanism from a chemical perspective. And then I will dive into two main pillars of aging mechanisms. And this is the experimental support that has been provided through different studies that we have performed via kinetics, oxidation kinetics, so evolution over time, and also the aging mechanism via standard lab protocols, which means that we used simulations in the lab, the so-called short and long-term aging by means of rolling film oven and pressure aging vessel. And since this is a menu should always include some food. And in this case, I have included some food for thought, which are actually the conclusions and recommendations out of this specific work that I will present in my speech today. To begin with, what is aging? Aging, as far as you know from your everyday life, is related with change of our skin, for example. In these two photos, you can see myself in two different years of my life, in 2006 and in 2022, so almost after 15 years. And as you can observe, a lot has changed in my face, for example. You can see some wrinkles around my eyes. And of course, this is what we call aging in human beings. So this is what we realize as people as the aging. Now, how aging of human beings is connected with bitumen, this black material that we use for our roads. We have some similarities with bitumen, and one of them is that both bitumen and also ourselves are made from organic matter, which means that we more or less we are composed from the same chemical composition. And besides this, we are both exposed to the oxygen of the atmosphere. These two factors together create what we call aging or oxidative aging. So both ourselves and bitumen, we are organic materials. We are made of organic materials, and we are exposed on oxygen that exists in the atmosphere, and is essential for us, for human beings, of course, to survive, because it's our main function of breathing, but also ages our skin. And in the case of bitumen, it also ages the bitumen which is part of the pavement together with the aggregates and filler, as you know, of the composition of a road. Now, the problem is that as time goes by, like the human beings, also the pavement, the roads age, and they start to create some crackings. Here, for example, you can see on the top right one image from close by to my campus here in Antwerp, that we observed some type of cracking, and this cracking is similar to what, for example, you can see in around your eyes as you age, similar to the wrinkles that people normally have, and of course, this is in another similarity with the distresses that asphalt roads have. Now, this phenomenon is called aging or oxidative aging. Of course, there are other factors that affect the pavement, like UV, the reactive oxygen species. But today I will focus in one main factor, and this is the oxidative aging, since this is considered one of the most important factors for distress types. So this phenomenon of aging has been studied from different scales, starting from the macro scale, so the real road, and going down to the meso scale, the micro scale, and the molecular or nano scale. When we are talking for micro and molecular scale, we basically mean the asphalt binder or bitumen, as I mentioned, that is called in Europe. And this is the scale that I will focus today to understand a bit better what happens in a chemical perspective for the aging mechanism and how this affects the bitumen. Now, for bitumen, this is the one that is the most important component of the asphalt, since this is made of organic matter, as I mentioned, and this makes it prone to oxidative aging. And for bitumen, we have used a kind of simplified way to understand the chemical fractions or the fractions, the polarity-based fractions. And this is based on the so-called SARA fractions. And these come from, of course, from the four names of saturates, aromatics, resins, and asphaltins. And this with increasing polarity, going from saturates to the asphaltins. Now, literature also has reported changes of mechanical and chemical properties of bitumen with aging. For example, it has been reported in the literature that with DSR, with the dynamic seriometer, we can observe an increase of the complex shear modulus, also with Fourier transfer infrared spectrometer or FTIR. We can see an increase of sulfosides and carbonyl functional groups with aging. And also we can see, for example, a decrease of penetration, which is an empirical property or a characteristic property of bitumen, and a decrease of phase angle with aging, and so forth, so on. So this refers mainly in the literature to rheological properties and to some extent to basic chemical indices like the sulfosides and carbonyls. However, it has not been studied thoroughly how all the chemical compounds in bitumen are affecting the aging mechanisms that have been hypothesized some decades ago. So with regard to the aging mechanisms of bitumen, it has been reported already 3 decades or more ago that aging can be distinguished into rate determining phases, namely a fast rate and a slow rate phase. Petersen, as you can see also the reference, also assumed that if we take a representative molecule of bitumen, for example, a dihydroathracene, and this is later oxidized from the oxygen that exists in the atmosphere, then after an intermediate hydroperoxide, we can have two possible chemical routes for the fast rate phase. Either this hydroperoxide is aromatized, and this is accompanied by the formation of sulfosides, or free radicals or if this hydroperoxide is thermally unstable, free radicals will be formed. And these free radicals, he also claimed that they can play an important role for the continuation of the slow rate phase, which in reality is the long-term aging that affects for years our roads. However, little experimental support has been provided for this hypothesis, and historically speaking, the scientific community started already in the 60s from the oxidation mechanism. So this hypothesis that I mentioned, they date back to the 60s. And then there were some individual researchers that studied oxidation kinetics with the goal, of course, to prove if these mechanisms are reasonable or not. However, then this was then shifted, the scientific community shifted to something that can be repeated rather quickly in the lab, and then the lab simulations were developed. And from 2000 and onwards, there were, of course, a lot of efforts to reduce specifically or to improve the rheological performance of bitumen, and to reduce or mitigate, let's say, the aging by introducing antioxidants or rejuvenators. And in the last few years, there is an increasing, let's say, trend of scientific community to couple the chemistry with the performance via the field of chemomechanics, as it is called. And this is also a field that also Dr. Rahman and Dr. Ding have provided support, especially for the microstructure of bitumen. So for my presentation today, the objectives in general of my research are focusing in different levels. For example, a common, for example, link that exists with the group of Dr. Rahman and Dr. Ding is the effect of aging on bitumen microstructure, and also some thermoanalytical properties that can also provide support or evidence for this microstructure. Also, my research is focusing on the link of chemistry with rheology, as well as the modeling of the aging mechanism. But for today, I will focus on the first objective, which is to support experimentally the hypothesis that was shown before with regard to the aging mechanisms of bitumen. And now I will continue with the main parts of my presentation. And the first main part is the aging mechanisms via kinetics. For this part, I used three binders, namely binders A, B, and C, as you can see on the table on the top right. And these three binders were varying significantly with each other. So binders A and B are from the same crude, and they vary completely in terms of performance. So the idea here was to choose three binders that they have differences between them, to see if we can really support these aging mechanisms, or they are based, for example, on the performance, on the characteristics of the bitumen. So binders A and B were from the same crude, but they were varying for performance indicators like penetration, as you can see, and other empirical properties. So A and B were straight run binders. The difference with binder C was that binder C was the result of fish breaking process, so the distillation process was different, and also it included waxes, paraffinic waxes in its composition, as was checked by differential scanning calorimetry. And also this bitumen C had similar performance empirical properties with binder B. So these three binders took into account both the distillation process, the type of bitumen by means of empirical properties, but also the existence or not of paraffinic waxes. And for these bituminous binders, what we performed is kind of modified thin film oven testing, or MTFOT as it is called. And this was a film of binders of these three bitumens of approximately 1 millimeter. And this was placed in a ventilated, air-ventilated oven at 50 degrees for different time intervals from 0 to 56 days. And then different spectroscopic techniques were used at the different time intervals. For example, a Fourier transfer infrared spectrometer, or FTIR, an electron paramagnetic resonance, or EPR, and a time of flight secondary ion mass spectrometry, or TOF-SIMS. The idea of these three techniques was that we were trying to prove, of course, the aging mechanisms, the hypothesis for the aging mechanism, by the formation of sulfoside that was reported by the SHRP report and Petersen and his colleagues in the 60s. The formation of radicals, as I mentioned, when the hydroperoxide is unstable, and also to understand what type of other chemical compounds can be formed. So the idea was, if we use these three techniques, we would be able at least to review the hypothesis for the aging mechanism. More details, of course, you can find in the reference that I provide below, which is one of our papers published in the previous years. Now, jumping to the results, as I mentioned, FTIR was studied in all the time intervals from 0 to 56 days, as you can see on the top left. And from this spectra of FTIR, we isolated the sulfoside area, and this was calculated and plotted on the right. And you can observe that all the three bitumens, bitumen A, B, and C, showed an initial rapid increase until approximately 7 days, which is considered as the fast rate phase, followed by an almost constant slope, which is the slow rate phase of these binders. So around 8 days, we have completed the fast rate phase independent of the bitumen source or bitumen type or distillation that we had for these three binders. And then for all of them, we observed that we have a kind of constant slope. So these data points were then fitted with a kind of Saido first order model for oxidation kinetics, as you can see the equation below. And all of them fitted well to such a Saido first order kinetics modeling, which also justified that from FTIR we can indeed confirm that there are two rate determining phases, namely a fast and a slow rate phase. Of course, the fitting factors can be shown on the table at the bottom of this slide. It should be noted also that sulfosides were more prone to be produced in this rather low temperature of 50 degrees that the modified thin film oven testing was conducted. And this is in line with literature that mentions that probably carbonyls are more prone to be produced when higher temperatures are used. The idea of using 50 degrees, of course, was based on the fact that we tried to simulate as close as possible, but also as fast as possible. Okay, perfect. Because I could hear back my voice. So the idea was that the 50 degrees was used in order to have a closer to reality, let's say, to real in situ conditions temperature. Also, as mentioned in the hypothesis for the aging mechanism, we could have also formation of radicals. EPR is a technique that can identify both radicals, but also unpaired ions. Of course, there were some challenges in the beginning because it was one of the first times that this technique was used for bitumen. And we experimented a lot with the sample preparation in the beginning until we have good repeatability and also an optimized sample preparation. And here you can see one of the spectra of binder of bitumen A, and in different time intervals. What we observed by comparing this spectra with characteristic tempo solutions, which are solutions that give the number of organic radicals that you can have, is that in bitumen we can identify in the spectra both organic carbon center radicals, but also vanadine ions, vanadyl porphyrin ions. And these two were then tracked on over time. So their kinetics were plotted. And you can see on the left here that the number of spins of the carbon center radicals, these are the carbon center radicals, were following again a more rapid increase in the beginning, followed by an almost constant slope or even a plateau as it can be seen. And this means that we tried again to fit them with the same model, with Saido first order kinetics model. And it was shown that if we feed it with the fast and the slow rate term, then the results also are not aligning with the idea of having having both parts, so a fast and a slow rate term. However, then we plotted it with a mono exponential term, so neglecting, for example, the second term of this equation. And this fitted pretty well in let's say, predicting the evolution of the organic carbon center radicals. What this shows us is that the rate of production and the rate of consumption of the carbon center radicals, around 8 days, it becomes equal. For that reason, we don't observe either an increase or decrease of these carbon center radicals. Moreover, the hypothesis of the aging mechanism claimed that we can have radicals that they are oxygen center radicals. However, the oxygen center radicals are rather living too short, so they are not able to be captured with such a technique. What we also assumed is that the organic carbon center radicals that we observed and we have captured are probably yielding from the oxygen center radicals, that they are short-lived, and most probably the rate of production of the fast rate phase is governed is the governing one for this evolution of the organic carbon center radicals. This means that we can still support two rate determining phases. However, here the fast rate phase is governing for the production of the organic carbon center radicals. Also, on the right graph here, you can see the evolution of the vanadine ions over time with aging kinetics, and we observed that we have almost stabilization of these vanadine ions. This is really important, especially for bitumen producers, because what we also tried later is that we found the correlation with the vanadine ions and the vanadium content of these three bitumens. And the vanadium content is considered as a kind of tracer of the crude. And as I mentioned, bitumen C was coming from a different crude in that case. So vanadine ions are almost unaffected by aging, as can be seen also considering, of course, the standard deviation that is given in this graph. So also from EPR, we were able to support two rate determining phases, regardless of the bitumen type, distillation, presence of wax or not, so waxy binders or not. So the two techniques together, so FTIR and EPR, were able to support the hypothesis of two rate determining phases, and also to prove that indeed we can talk for formation of organic carbon center radicals that were captured one of the first times that was reported in such extent with kinetics. So the transition point from the previous graph and from FTIR was found around 8 days. So 8 days, and the transition point is the completion of the fast rate phase, of the rapid phase, and the initiation of the slow rate phase. So 8 days is considered as the transition point for all the binders based on this study. So we used then another technique, the time of flight secondary ion mass spectrometry, or TOF-SIMS, and this spectroscopic technique is useful in order to have so the principle is based on the fact that the bitumen film is bombarded with bismuth ions, and the emitted ions give information for the fragments of bitumen. And we were able to classify all the fragments in sulfoside containing and oxygen containing or hydroxide containing fragments. And these are all the molecular assignments that were observed for all the bitumens and were grouped later in these two big categories. Going to the results, it shows that we have an increase of all the sulfoside containing fragments, which is in line with the hypothesis of sulfoside formation, and also an increase of the hydroxide containing or oxygen containing during the fast rate phase. So it was studied at 0 and 8 days, which 8 days is the completion of the fast rate phase. The second graph on the right also shows that we can have an formation of different type of OH containing fragments, and this can be not only carbonyls but also other types of chemical compounds like alcohols that has been also hypothesized by other researchers in the past. Now, also TOF-SIMS can give high resolution images, which is a kind of chemical mapping. And for one of the binders, the waxy binder, we saw that before and after the fast rate oxidation phase, from the right column, there is a decrease of the aliphatics, and this can be was later correlated with, because in waxy binders we observed the so-called B structures, was also related with the reduction of the B structures. And this, of course, had also some difficulties in order to identify, because the waxes were related with the aliphatics, the true impact of the chemical compounds for this waxy binder. However, in reality, as we know, we don't use aging kinetics in the lab, but rather standard simulations of rolling thin film oven testing, or RTFO, followed by pressure aging vessel, or PAV, that simulate the short and long-term aging. So the same spectroscopic techniques and the same binders were used in order to identify what is the effect of lab simulations in that case in the aging mechanism, and the results, more details of the results can be also found in this publication. The results from FTIR showed, as expected, that we can have an increase of both carbonyl and sulfosides with aging, and the two straight run binders coming from the same crude, so the binders A and B, showed similar increase of sulfosides in the lab. This is something that, of course, has been reported several times in the literature. Additionally, we observed that from FTR spectra, if we isolate the branch aliphatic functional groups and the aromaticity index, these were from this analysis were almost unaffected by aging, since this was stable, as you can see. So this means that the hypothesized aromatization that hydroperoxides could have cannot be captured with FTIR. For that reason, we used later also the electroparamagnetic resonance in order to see how the radicals can be captured. And from the left graph, you can see that we can have for all the binders an increase between the unaged state, so the fresh binder, and RTFO, and then we have a kind of stabilization of these carbon center radicals for binders A and B more specifically. And this again means that between RTFO and PAV, we have reached this plateau that was also observed in the kinetics. So we have reached the slow rate phase of a possible oxidation scheme. The vanadil also species were again considering the standard deviation almost stable with aging, and this again confirms the idea that this can be used as a tracer of the crude. Complementary, we used protonuclear magnetic resonance, or HNMR. HNMR is a kind of can be used in bitumen as a kind of chemical fractionation besides the polarity-based fractionation of SARA. At the bottom, you can see a typical spectrum of bitumen, and this was dissolved in deuterated tetrachloroethane, and the results was then used the areas, of course, omitting the solvent peak of tetrachloroethane in 5 different proton regions of methyl, methylene, alpha alkyl, olefinic, and aromatic. And these were studied in terms of aging with RTFO and PAV. And we observed from these results that bitumen A and B that were coming from the same crude showed the same chemical fractionation or proton distribution in the unaged, but also after aging. And for all bitumens, there was an increase of the methylene proton region and a decrease of alpha alkyl region. So this provide more, let's say, strong information for the differences in chemical fractions of bitumen with aging. Finally, TOF SIMS was used before and after long-term aging with PAV. So the findings showed that the hydroxide-containing fragments were increasing for bitumen A and B, whereas this indicates also that products like alcohols can be formed after PAV. Also, for bitumen A and B, we have formation of sulfoside-containing compounds, as you can see on the right graph, whereas bitumen C probably didn't show the same trend because of the aliphatics that covered most of the bitumen surface, as was shown previously in high-resolution images. Moreover, other chemical compounds like polycyclic aromatic hydrocarbons were increased with aging for bitumen A and B. And also we had the slight increase of aliphatic ions, whereas the intensity of aliphatics was the highest for bitumen C, which I recall that this was the waxy bitumen. And again, an association with the wax-related particles and aliphatics can be found. And later this was used also for microscopic purposes. Bitumen C was also more complicated because of the waxes, so more advanced analyses were used. First, we separated the bitumen in asphaltins and maltins. The results of these publications in Fuel can be found also in this reference at the bottom of this slide. And it was shown that the asphaltins, as studied in FTIR, were more oxidized, followed by the parent bitumen, and parent bitumen is the bitumen C. And also differential scalar calorimetry showed that the wax was found in the maltins rather than the bitumen, especially after long-term aging. And this has an association with what one mentioned before for the aliphatics that were found via TOF SIMS. So this brings me almost to the end of my presentation, where I would like to summarize the today's specials, since this was a menu as I promised. What is important is that we use several techniques, experimental techniques, some of them rather not so often utilized, let's say, for bitumen. But we should always take care that these give different information sometimes. And with different information, I mean that they, for example, give information in different depth of the bitumen, comparing, for example, the TOF seams with the FTIR. Besides this, we were able to support indeed two-rate determining oxidation phases, as mentioned some years ago in the literature, and also to prove that radicals are formed and they evolved during the fast rate phase, regardless of the bitumen type, because we had different types of bitumen and distillation process. And we also proved that some products, chemical products, can be formed like sulfoside and oxygen-containing compounds, especially also after long-term aging. And also that there was an increase of aromatics and decrease of alymphatics only for the wax-containing binder. So what you can take as a message with you from this presentation today is that we can target as researchers and you as students in your master thesis, or if you continue your PhD studies, to use more state-of-the-art techniques. So besides common techniques for complex phenomena, we really need to turn to more sophisticated techniques that were not used before in bitumen. Also, we should be able to link this information with the performance at the end. So the chemistry should be linked with the rheology of bitumen, since we should also couple the chemistry with rheology for engineering purposes. So from this presentation, what is important is that for contractors and authorities around the world, we should propose as a community, as a scientific community, is a database that we can have in situ binders. In situ binders means binders extracted and recovered from asphalt cores, because this includes all the information as it happened in reality. Whatever we will try in the lab, oxidation kinetics or lab simulations, still they are not capturing all the effects of aging that happens in situ, in the real road, in the field. And for bitumen producers and suppliers, this presentation and these results are important since they are using new additives or biomaterials or rejuvenators. So they should take into account the chemistry and what compounds, for example, they should be reduced in an ideal bitumen, or what additives should be added, for example, to mitigate aging. I would like to thank you for your time. And of course, in case that you have any questions, you can always email me. This is my contact email. And in case that you are interested in the list of publications that I mentioned and also other from my studies, you can also scan this QR code, or you can always contact me to provide you with any publication. Thank you very much again for the invitation today. And maybe if there is still some time for questions and answers, I would be glad to discuss it.
Okay, thank you. Thank you so much, Georgios, for very nice presentation, very informative and very deep research. I know it's a part of your research, what you have done since your PhD till now, and very deep, very advanced, and using the as you mentioned, some in fact, going toward this stage that we need to use more advanced equipments or research equipment to really understand how the aging mechanism in asphalt is going to have in terms in chemistry, in terms of chemistry or other mechanism that is happening during the aging period. I think they're very informative. I want to, among the audience, if anyone has any question, please, you can directly raise your hand and ask your question directly from Georgios, or you can type on the chat box and I will read the question. Okay.
Hello, Georgios. Yeah, I have one. I have two simple questions. Yeah. Because in your presentation, you didn't mention how you age your sample, like use tradition, like standard PAV, using thick asphalt film. Yeah, or use some thin asphalt film, because I know in Ontario, in Canada, Ontario, they recommend to use thin like asphalt film to simulate the long-term aging, and they also recommend to use some moisture in the PAV to accelerate the oxidation of the asphalt. So do we have any like idea about how to better simulate the aging of our asphalt? Thank you.
Yes, thank you for your question, Dr. Dink. That's a really nice question, because we were investigating that in a parallel study that, of course, I didn't have the time to present today. So the kinetics were done with a thin film of 1 millimeter. So we had a film applicator, let's say, that you can make really thin films in the lab. And we have this thin film in the oven at 50 degrees. So this is how we studied the kinetics. For the short and long-term aging, we used RTFOT. The RTFOT, we used the standard protocol the standard protocol, the European standard protocol, because the American one, for example, has also different time. In our case, it's at 163 for 60 minutes in Europe. And the PAV, we used the recommended protocol in Europe mentions that it should be at 100 degrees for 20 hours and with a thin film of, I think, 1 centimeter. So it's rather thick, I think, for 1 centimeter, but the idea was, because always as researchers, we have, to persuade also the contractors and the authorities. And why we did that with the standard protocols is because we wanted to see how the mechanisms are changing with the protocols that we are using nowadays. So the idea was to first use a more sophisticated, from our side, let's say, preparation of samples. So we used thin films of 1 millimeter, and then we compared the results with lab protocols. In a parallel study, also, we used different film thicknesses and humidity. And this was in collaboration with the colleagues at TU Delft, that some results were published or were presented last year in the AM3P conference by my colleague. But then we saw also that there was an effect of the thin film. If it is 1 millimeter, 1 centimeter, this plays a role on the products, especially on the intensity of the products.
Okay, thank you, Georgios.
Yeah,
and I have one more question.
Sure.
Yeah, because we know asphalt have different aging mode, like oxidation, physical hardening, UV aging. Which one do you think more important, or can you rank them? I think when I write a paper, many reviewers ask this question. Sometimes because we are focusing on physical hardening, and sometimes the review ask, okay, maybe this is not important, but actually in Ontario, in Canada, they say, okay, this is very important. So sometimes I'm confusing about this. We are also focusing on this. We compare different aging mode, like which one we want to see, which one is more important.
Yeah, of course, everyone that works with a specific one probably claims that is the most important always. But yeah, I would say that, of course, there are some. So if we, let's say, try to rank them, which is a really difficult task, I think, it depending on what you are. For example, for me, if there are no waxes in the bitumen, doesn't really make sense to study so much the physical hardening. So what you are studying is also dependent on the type of bitumen or binder, let's say, that you have. For waxy binders, it makes a lot of sense, of course, to study the physical hardening. But also most of the binders, they have waxes. I mean, it's difficult to find a crude that doesn't have waxes already in the crude, not even in the distillation, that it can create additionally waxes. So just maybe to give a diplomatic answer, I don't think that there is a best or worse. It's really based on what type of binder we really target. So if we study waxy binders, I think that physical hardening is the most important. If we study non-waxy binders or binders with low melting enthalpy, which it shows also how much wax you have, then I think that oxidative aging is important. But on the other hand, there are researchers, probably you know, in Austria, that they study now the reactive oxygen species, how they affect the aging mechanisms, which is, of course, another factor, as well as the UV light. I mean, of course, we need to simplify sometimes things to study the research. So, yeah, I think, yeah, there is not a clear answer for which is the most important, let's say.
Yeah, thank you. Thank you very much. Thank you.
Thank you. Thank you so much, Aiba. Okay, any other question? You can raise your hand and just ask your question directly from Georgios. Yes, Han Liu, please. Okay. We don't have your voice. Let me, yes, yeah, you can talk. We don't have your voice here. No, not.
Maybe,
Okay, yes,
want...
yes, that's right. Yeah, we are hearing you. No, again, we missed your voice. Yeah, this is okay. No. It seems.
Maybe do you want to type it, Han, in the chat? Because I'm not sure what goes wrong with the microphone.
Yeah, your mic, I think there is some issue with your mic. You can type your question in chat box. Okay, so while he's, I think, typing his chat, his question, I have a question, Georgios, for your from my opinion. In fact, so I know the aging, the different types of aging processes, or as you mentioned, is evolving, and there are a lot of research that need to be done to really figure out how the aging phenomenon can be controlled or postponed or avoided. Maybe in it to be idealistic as a pavement engineer, but I want to know, although you've done a lot work on for the binder phase during the binder or aging, I want to know whether have you done any research or you are gonna in future start any research to in fact evaluate the aging in upper level phase, such as mastic phase or mortar phase, to see really how aging body burn it's a mix with mineral or other aggregate, how it's really gonna influence the whole matrix, whether it is mortar or mastic, or even finally at the end mixture, because we are in reality what we see or what we will apply is the mixture. Is not, of course, aging of the binder is something that should never neglected, but something that finally is going to be deployed on the road is the mixture that we are facing, and it should be at the end we are talking about the aging of the mixture. So I want to know what really the trend is going to, if based on your perspective. This is my question.
Yes, for sure. This is something that is really important, and I think a lot of researchers have stressed that. Okay, what is of course the purpose of studying so much in detail the chemistry? And of course, as engineers, we really need to think how at the end we'll apply in a practical level, let's say, so in mastic, mortar, or even in asphalt mixtures. So what I can say is that we have tried until now only in the mastic level to compare our results, let's say, especially for the kinetics evolution. We tried that by gravimetric, let's say, techniques to see how the mastic changes, for example, with oxidation. But the problem with having a more, let's say, complicated structure, I mean, to have fine aggregates and filler, is that in that case, it's difficult to have chemical information rather than some crystallographic properties or something like that. We cannot talk for chemical compounds anymore. And aging, in reality, my, let's say, idea is that the main factor that affects aging is bitumen. And because bitumen is the one that is oxidized. Of course, when bitumen is oxidized, then it changes the adhesion and cohesion with the other components like aggregates or filler. But when we want to see the mechanisms from a chemical perspective, we should focus on bitumen. If we want to see it, the mechanism from a mechanical perspective, then we come actually to what you said, Dr. Rahman, to more upper levels of mastic, mortar, or mixtures. In that case, we can only perform, of course, more mechanical testing or rheological testing, and not really chemical testing. But having an idea on the adhesion, for example, what I believe, especially now, and I really recommend to my PhD students, is that they should focus basically on the adhesion of the bitumen with the aggregates. And for that, for example, there is the Cecil drop method that can be used, which is, I'm not that familiar. I have not used it in the past, but I have seen a lot of people using that in papers. And I think this is quite important to understand first the link between the aggregate and the bitumen, and then, of course, having some rheological testing, like mortar testing in DSR or mastic.
Okay, thank you. Thank you so much, Georgios, for your answer. Very full and detailed. I know we are running out of time because Hanley already typed his question, and he asking, is the aging process of asphalt a reduction in compatibility of internal components or a transformation between different internal components? Is
Okay.
this? Yeah.
Thank you very much for the question, Han. That's also a difficult question, I would say, and more in depth. So this comes basically to the idea of what type of structure, let's say, you will consider internally for the bitumen. So as probably you may have read, there is the so-called Yen-Mullins model that is based on asphalt in nanoaggregation. And let's say if we consider this model, then indeed we are talking for the second part of your question, for transformation between the different internal components, because this model actually believes that we can have, let's say, aggregation of asphaltenes or making clusters. And these clusters also change, let's say, the mobility of the molecules later. The reduction of compatibility of internal components is going more to another type of model or theory, let's say, for the structure, the so-called dispersed fluid theory, which can also be true. I mean, there are some studies really more advanced, I think, that they used, but I also, Dr. Dink and Dr. Rahman used at some point the small angle X-ray and other diffraction techniques. So these techniques probably are really useful to understand if we really talk for reduction in compatibility or for transformation of the different internal components. What we can also additionally say here is that what can be helpful is to have the different fractions, the so-called SARA fractions, to understand if, for example, aging changes in terms of quality of the fractions. And in that case, you need the fractionation technique that will give you the 4 fractions, and you can individually study each fraction, for example, in a chemical analysis like in FTIR even, and see if the quality of the fractions changes. This will tell you also if we have a transformation of the components or it is just a reduction of compatibility. That's my idea on your question, Han. I'm not sure if I satisfied you, but thank you also for the question. That's also for me really enlightening.
Okay, thank you. Thank you so much, really, Georgios, for your time, for your insightful presentation, and for your answers. That was really very helpful. And I hope our students could get some idea, and also for those who are also interested to work in the aging mechanism of binder or bitumen, they can get more, in fact, some insights, some idea, or maybe for their future research they might face during their research process. And really, thank you so much again, Georgios, for accepting our invitation. It was a great pleasure to have you, and we are very looking forward, maybe hopefully, whether you or your group, to have this kind of exchanges or academic seminars in future, and hopefully we will have more collaboration and in research.
For sure.
And
For sure. Thank you once again for the invitation, Dr. Rahman and Dr. Dink. And of course, for me, that's, let's say, a starting point for further collaboration. So if you have already identified some aspects that we can collaborate, or we can have a common experimental plan, we can, of course, discuss it later. And of course, for the students, maybe I'm not sure in which year of their master's or bachelor's they are, but so I'm not sure if it was too deep or not. But if someone is interested and is willing, for example, to visit us for his PhD or master thesis later, we are always open to collaborations. And if you need also, I can share my presentation later, Dr. Rahman, so that you can distribute it to the students if it is interesting.
Sure,
Thank
sure.
you.
Thank you so much.
Thank you very much.
Thank you. Yeah, thank you. Sure. We are again to our audiences. This session is being recorded. We will share with you the recorded link, and also when I get the presentation, the PowerPoint, the PPT file from the Georgios, I will share it with you. Okay, so with that, I will wrap up our today speech and presentation webinar. I hope we are, by the way, I have to again add that we are gonna have more webinars like this, like today presentation, and which we will be inform you on in a timely manner. Thank you everyone for your attention, and wish you have a great day. Thank you, Georgios, and bye-bye. Have a nice day. Thank you. Thank you, everyone. Bye-bye.
Thank you. Bye bye.